So Unit 2.2 and Unit 2.3, we're going to go into a little more detail about mostly the ionic compounds, but we're going to look at some of the things about the solids. And we're also, I guess, we're going to also visit how do these atoms come together to form one of these bonds, ionic or covalent. So in bio, you didn't really learn it this way. So we have to kind of change one of your misconceptions here. But when you guys talked about ATP and ADP, losing a phosphate or gaining a phosphate, you looked at the overall series of equations, but not each individual one. And so a lot of people kind of get this incorrect. So we're going to kind of change this up for you. If you break a bond, a carbon-carbon bond, a carbon-chlorine bond, a sodium-chlorine bond, any atomic bond, that bond has to absorb energy. If you form a bond, energy is released. And I think most people from bio get this mixed up. So think about if you had a pencil. Here's your little pencil. Not a very good looking pencil there. Eraser. If I would try to break that pencil, would I have to give it energy or would it release energy? For me to break that pencil, I would have to give it energy. So energy has to be absorbed by that pencil. No, pencil is not a bond, but it might give you a little something you can kind of visualize. This graph is a very, very typical graph in AP chemistry. I would say almost 100% chance you're going to get this on my test and also on the AP test in May. And you have to be able to kind of understand what's going on with this graph here. So we have, let's go red here. So we have a couple things. One, you know what, actually, let's use this. We have potential energy, and then we have distance. So distance between two atoms. So it might be kind of common sense. It may not be common sense. We'll see. But if you have, let's make this an ionic compound. It might make it a little easier to visualize. Think about it as almost like magnets. If you had a positive and negative end of two magnets, if they were, you know what? Let's not use magnets. Let's just think about if you had some sort of thing that was too far away from each other. No matter how much they would like to attract, they can't attract. So if the distance is too far apart from each other, they just don't have the ability to attract. So no bond is going to form because they're just too far apart from each other. So that's more about the distance. If you get them too close together, even though they're neutral atoms, you might get to the point where the nuclei are so close together and the nuclei possess protons that you would repel. Those two atoms are too close together, they repel each other. So no bond is going to form there either. So if you put two parts of a magnet together, two magnets together, they're positive, positive, negative, negative, you actually have, there's a lot of energy there to bounce those two magnets apart from each other. So that's sort of why it's up here on this potential energy. Why is this down here at this very bottom of potential energy? Well, let's go back for a second. Bonds that are formed release energy. Release energy. So if you release the energy, you don't have potential energy left. So if you get to the sweet spot where these two atoms are not too close, not too far away, just in the sweet spot, they can form a bond, potentially form a bond. And if they do form that bond, energy has to be released. If energy is released, it's going to bottom out on this graph and get as low as it possibly could get. And remember that a single bond has some energy, meaning that if you form a single bond, it's going to release some energy. If it's a double bond, it's going to release more. If it's a triple bond, it's going to release even more. So if you had, let's go another color here. Let's go. Maybe we'll go this color. If you had another one of these graphs and it bottomed out even more, well, guess what? This compared to this one might be the difference between a single and a triple. The triple bond would have to be that one, and the single bond would have to be this one. Now, I may have not gotten this right on my x-axis. I was just trying to show you the y-axis part. The distance, remember when we talked about the triple bonds, the distance between the two atoms actually is going to be lower. So I think I erred. I probably should have had this hump a little bit over on the left. But you get the idea as far as the y-axis on there. And we'll revisit some of these in class. We'll have a few more questions that deal with that. Okay. So how do they figure these things out, these internuclear distances, and some other things about molecules and about sizes of atoms and things like that? Well, they use something called spectroscopy. I mean, this isn't the only thing they have available to them, analytical chemists, but this is one of the things that they use. And we're actually going to do some spectroscopy in our class too. We are going to use visible radiation. That's like Roy G. Biv. Red, orange, yellow, green, blue, indigo, violet. You could go into the UV radiation. You could go into infrared. You could go into microwaves. What else do we have here? We have X-rays. Those are all very useful spectroscopies. We're not going to do all those in class. We're just going to again go with electronic. And why would you use each of these? Well, we already talked about mass spectroscopy. That's where you're trying to figure out the abundance of certain types of isotopes to get average atomic mass units. We already did PES. That's where you can look at how much energy is associated with losing electrons from different shells and subshells. We haven't talked about vibrational yet, but you can, well, we're talking about it now. We can use that to determine the type of bonds, the distance of the atoms between the bonds. And then you can look at also this rotational to figure out geometries. So, for instance, oxygen and hydrogen have a bond angle here of 104.5. Well, how did that get figured out? With rotational spectroscopy. So it doesn't take very much energy to rotate an atom, a molecule. So you don't need to use very much energy. Microwaves actually have very little energy. Infrared, a little bit more energy. So if you needed to do more than just rotate, maybe you need to vibrate atoms for understanding something, then you might need to use infrared. If you wanted to use, if you wanted to figure out something else about a compound, you might need more energy. Well, these possess more energy. If you wanted to get rid of electrons out of an atom, it's going to take a tremendous amount of energy, photoelectron spectroscopy. And then this is even requiring more, and we don't even get into the type of energies associated with that. Okay. We've talked a little bit already about lattice structure, and I guess that would be about these ionics. So it's a repeating structure. Na positive, Cl minuses in this case. Or we talked about covalent, where you share electrons either equally or unequally. And then we didn't talk about metallic. This will be for another day. But anytime you have these atoms connected to each other in some kind of bond, we're going to call that intramolecular. As opposed to later on, we'll talk about intermolecular, and that's going to be between molecules. So maybe if you had H2O, and how it would like to attract another H2O. So we won't be talking today, we're talking about those bonds right there. And then for another day, when we get to intermolecular, we'll talk about, people often use these dotted lines between two molecules. And again, our old friend Coulomb's law. In this case, as we talked about last time, lattice energy. So we got the charges of the ions, and we have the distance away from those ions from each other. And if you wanted to compare maybe how does NaCl, what kind of attraction, what kind of lattice energy does it have, as opposed to maybe calcium with chlorine. Well, calcium has a +2 charge, so it doesn't really matter which Q you're looking at. But one of these Qs is going to be double the charge as opposed to the other. So it's going to give it tremendous more lattice energy. This one would be even more if you had like a aluminum with chlorine. So a +3 gives you even more Q. Yes, the R or R squared is going to be different, but not as different as the charges. So we're going to look at charges, the Qs, before we look at the distances between those. And this just describes a little about the lattice. They're rigid, orderly, they repeat. They call them unit cells. We don't have to really go into that in our class. You might take other chemistry classes where you go and do that. But if you want to study all that, you have to use X-ray diffraction. X-rays have a good bit of energy, and you can bounce the X-rays off, and they come back in different angles. And if you study those angles, you can figure out things about that lattice structure. Here are a couple ionic crystals here, and they all have different properties. Different melting points, different boiling points, different geometries, different crystal looks to them. But you learned this in first year chem. They don't conduct electricity by themselves, but if you dump them in water and they dissolve in water, they become ionic. Well, they have ions that are in the water and they're mobile, so they can conduct electricity then. And here again is a typical one, NaCl. Here's our repeating lattice. You can either look at the right or left one there. And then you could go into lots of things with crystals. I just plucked a few of these out from the internet. They often have really interesting looks to them and properties. A lot of them will have special light properties, give them different colors. Maybe they have some imperfections that give them a green hue or blue, whatever. A recommendation would be, if you have a chance to go to the Carnegie Museum down in Oakland, they have a really nice crystal area there. I can't be certain they have any of these. What do we got? 11 here, but they very well could. But they definitely have a really neat gem collection there. Okay, I think that might be it. Yeah.